Lipids, Chapter 26. Objectives: 1. Introduction to lipids. 2. Complex lipids. 3. Simple lipids. Goals: by the end of the chapter, you should be able to understand lipid characteristics, know the lipid subcategories, know key lipid reactions. 1. Introduction to lipids. It might be necessary to review the following topics to prepare for the material in this chapter: partially hydrogenated fats, autooxidation and antioxidants, base catalyzed hydrolysis of esters, saponification. Lipids defined. Lipids are naturally occurring compounds that are soluble in nonpolar solvents, or they're hydrophobic compounds. Complex lipids readily undergo hydrolysis under acidic or basic conditions to produce smaller fragments. Simple lipids do not undergo hydrolysis. Lipids are the only class of biomolecules that is not based on functional groups, only solubility. Subcategories of lipids. Lipid subcategories have structural similarities. We saw earlier that complex lipids can be hydrolyzed, and these will include waxes, triglycerides, and phospholipids. Simple lipids cannot be hydrolyzed and will include steroids, prostaglandins, and terpenes. 2. Complex lipids. These are lipids that can be hydrolyzed, which we saw earlier include waxes, triglycerides, and phospholipids. Waxes are compounds that have high molar masses and their esters. Hydrolysis of a wax will yield an alcohol and a carboxylic acid. Waxes only differ in the length of the carbon chains on either side of the ester, and they serve a variety of functions in living systems. One use of waxes: triglycerides. Triglycerides are triesters that are formed from glycerol and long-chain carboxylic acids, also known as fatty acids. Triglycerides are generally used for long-term energy storage, storing about 9 kilocalories per gram of energy versus only 4 kilocalories per gram when we consider carbohydrates and proteins. Fats are triglycerides that are solid at room temperature. Oils are triglycerides that are liquid at room temperature. Fatty acids are the reason why. Fatty acids are 12 to 20 carbons in length. They can be saturated, which means only C single bond Cs, or unsaturated, meaning there's at least one double bond between carbons. The shape of the fatty acid will impact its melting point. More linear side chains pack more closely, resulting in a higher melting point. And here are some melting points of common saturated and unsaturated fatty acids. The saturated fatty acids will have higher melting points than unsaturated fatty acids. Higher molecular weight will also result in higher melting points. The trends are the same for the triglycerides. Fatty acids in triglycerides. The fatty acids found in triglycerides are often different. In this table, here is the fatty acid composition for several fats and oils. Animals have higher concentrations of saturated fatty acids compared to vegetables. Reactions of triglycerides: hydrogenation. Unsaturated triglycerides can undergo hydrogenation. A saturated triglyceride is obtained from the complete hydrogenation of an unsaturated triglyceride. That just means reaction with hydrogen gas in the presence of a catalyst. If only partially hydrogenated, some of the C double bond Cs can isomerize. That means it can go from the cis alkenes to the trans, and that is how trans fats are produced. Margarine is partially hydrogenated vegetable oil. The reaction is stopped once the desired consistency is achieved, but it also results in trans fats. Reactions of triglycerides: autooxidation. Unsaturated fatty acids are susceptible to autooxidation at the allylic position. A hydroperoxide is formed. This proceeds via a radical mechanism where oxygen gas in the air acts as the initiator. Recall that the net reaction is the sum of all the propagation steps. Reactions of triglycerides hydrolysis. Aqueous base yields glycerol and 3 carboxylate ions. Recall that this process is called saponification. Base catalyzed ester hydrolysis is nucleophilic acyl substitution. There's a nucleophilic attack. Hydroxide functions as a nucleophile and attacks the carbonyl group. There's the loss of the leaving group. The carbonyl group is reformed by expelling an alkoxide ion as the leaving group. And then proton transfer. The carboxylic acid is deprotonated by the alkoxide ion, generating a carboxylate ion. Soap consists of the fatty acid carboxylates obtained from saponification of triglycerides. And here is an example of what a soap would look like, or a soap molecule would look like. The polar group is hydrophilic, the nonpolar group is hydrophobic, and it's a sodium salt. The carboxylates then form micelles around nonpolar particles and allow them to be rinsed off with water. Reactions of triglycerides biodiesel. Transesterification of triglycerides can be acid catalyzed or base catalyzed. Biodiesel is made this way. Acid catalyzed mechanism is analogous to acidic hydrolysis. There first will be a proton transfer. Protonation of the carbonyl group renders it more electrophilic, followed by nucleophilic attack, and alcohol functions as a nucleophile attacking the carbonyl group. Proton transfer once again. The positive charge is removed via deprotonation. Proton transfer, the alkoxy group is converted to a better leaving group. Loss of that leaving group then. The carbonyl group is reformed by expelling an alcohol as a leaving group. Proton transfer, the positive charge is removed via deprotonation. Phospholipids. Phospholipids are ester-like derivatives of phosphoric acid. Most phospholipids are phosphoglycerides. The simplest phosphoglyceride is phosphatic acid and may ionize. The most abundant phosphoglycerides are phosphoric diesters. The identity of the alkoxy group can vary. Cephalins derived from ethanolamine and lecithins, which are derived from choline, are among the most common. Phospholipid bilayer. In water, phosphoglycerides form a lipid bilayer. The polar head is on the outside and the nonpolar tail is on the inside. To form a bilayer, the nonpolar groups must be able to pack closely together. 3. Simple lipids. These are the lipids that cannot be hydrolyzed. Steroids mainly function as chemical messengers. All steroids possess the ABCD ring system. It's a tetracyclic skeleton of steroids. They are rigid and the trans-ring fusions prevent ring flipping. Cholesterol is an example of a steroid. Cholesterol is biosynthesized from squalene. The rigid structure of cholesterol allows it to act as a stiffening agent for cell membranes. Some steroids function as sex hormones. These will regulate tissue growth and reproduction processes. Male hormones are androgens. Female hormones are estrogens and progestins. All 3 types of hormones are found in both women and men, but not at the same levels. Estrogens and progestins inhibit ovulation during pregnancy, and synthetic hormones have been designed to mimic estrogens and progestins by inhibiting ovulation and are oftentimes used as birth control. There are also steroids that are adrenocortical. These are hormones that are excreted by the adrenal glands. Cortisone and cortisol are used therapeutically to prevent inflammation and treat skin conditions. Prostaglandins. These are found in all body tissues and fluids. They contain 20 carbons, 5-membered rings with 2 side chains. They regulate many different functions, including blood pressure, clotting, inflammation, kidney function, heart function, etc. They do have their own set of nomenclature rules. PG indicates the compound is a prostaglandin. PGAs, PGBs, PGCs have a carbonyl group and an endocyclic C double bond C pi bond. Here are the examples of PGA, PGB, PGC. PGDs and PGEs are beta hydroxy ketones. PGFs are 1,3-diols. PGGs are endoperoxides. So here are all of these examples. PGE2 is responsible for muscle contractions during childbirth. And here's an example of that, prostaglandin. Classification. Prostaglandins belong to a larger class of compounds called eicosanoids, which are all derived from arachidonic acid. Terpenes. Terpenes are widely diverse groups of compounds. All terpenes are assembled from isoprene units. This is what an isoprene unit looks like. The number of carbon atoms must be multiples of 5. Here is a 10 carbon set of examples. Each one has 2 terpenes or 3 terpenes, respectively. Lots of terpenes are isolated from plant oils. They have a strong fragrance and are used as flavorants and odorants or in food and cosmetics. Menthol, camphor, and arcarbone are examples. Terpenes biosynthesis. Terpenes are biosynthesized from the following compounds, but not isoprene. The pyrophosphate OPP group is a good leading group. Biosynthesis mechanism. The reaction between dimethylallyl pyrophosphate and isopentyl pyrophosphate yields geranyl pyrophosphate. Geranyl pyrophosphate is the precursor for all terpenes. And here is the mechanism. There's the loss of the leaving group, nucleophilic attack, and then proton transfer. This will result then in all monoterpenes biosynthetically made. This is our last mechanism. This is our last mechanism.